All right, we got a short video here, just a couple things to go over. First thing is excited state configurations. Remember, excited atoms are atoms that have one or more electrons in energy levels above the ground state. So let's start off with a simple ground state configuration. We'll use hydrogen. So what this tells us about hydrogen is that there is one electron, so that's what this superscript here means, one electron in the first energy level, and that happens to be in an S sublevel. So what is a possible excited states configuration for hydrogen? How can we show that hydrogen has its one electron, only has one, it's one electron in a higher energy level than in the ground state? Let me give you an example. So I put a little asterisk there to indicate that this is not a ground state atom. This is an excited atom. So how about this, 1s2? Would that work for hydrogen? Well, you need to know what those numbers represent. So what this electron configuration tells us is that hydrogen has 2 electrons in the first energy level in an S sublevel. And that is not correct. Hydrogen only has 1 electron. So what are some possibilities? And there's lots of possibilities for hydrogen. How about that? What does that tell us about where the electron in hydrogen is? It has 1 electron in an S sublevel in the second energy level. Well, normally that electron exists in the first energy level. Here we're showing it that it's in the second energy level or higher energy level than in the ground state. This is a possible excited state configuration for hydrogen. Pause the video, list some more, and then we'll compare. So what did you get? We have 3s1, 4s1, 5s1, anything that shows hydrogen's 1 electron in a higher energy level than the first energy level. Let's make it a little bit more complicated. So again, you don't have to get too creative with your excited state configurations. The easiest and probably the best way is just to take the valence electrons, because it technically could be any of the electrons, but take the valence electrons and show them in a higher energy level. So go ahead and pause the video, give a possible, and I say possible again because there's many possible right answers. Pause the video, give a possible excited state configuration for lithium. So maybe 1s2, 3s1, or 1s2, 4s1, something that shows the valence electron of lithium in a higher energy level than the second energy level. So 1s2, 3s1 would work. Let's try one more. Go ahead and pause the video, give a possible excited state configuration for carbon. So notice this time I didn't bump up all of the valence electrons. I just took the 2 electrons in the 2p sublevel and put them in a higher energy level, in this case the third energy level. Something that confuses students sometimes is they think that this is not the electron configuration for carbon. It still is. The best way of determining what something is given its electron configuration is to count the electrons. So you can't go wrong by counting the electrons. Some people would think that this is silicon's electron configuration because it ends with 3p2, just like silicon's does, except silicon has 14 electrons. And all we have shown here are 6, so this must be carbon. Let's do one more. Go ahead and pause the video, give a possible excited state configuration for sodium. So maybe you got something like this. I just took the valence electron, which normally resides in the third energy level when sodium is in the ground state, and I bumped it up to the 5th energy level. Now you can't just, do 100th energy level or something like that, so don't make it too crazy. So maybe, just 1 energy level higher than the ground state, or maybe a couple at most. So that'll be good enough. So there are some examples of excited state configurations. Next up, what we're going to do is, using the orbital diagram for an atom, we can predict the charge of its ions. Let's do this. Go ahead and pause the video and write the orbital diagram for sodium. Pause it now, please. So here's the orbital diagram for sodium. So now something to keep in mind is that when a metal forms a cation, it does so by losing electrons. Now, they can't just lose any electrons. The easiest electrons for an atom to lose are its valence electrons. So when a metal atom forms a cation, it will do so by losing one or more, as we'll see in a little bit, one or more of its valence electrons. In the case of sodium, there's only one possible ion that forms from sodium. And so let's do this. Go ahead and circle the valence electrons in sodium. Pause the video, circle the valence electrons in the orbital diagram. So in the case of sodium, it has one valence electron. It will ionize by losing its one valence electron. So sodium forms an ion with a +1 charge. All right, let's try something a little bit more complex. Draw the orbital diagram for aluminum. Circle the valence electrons and indicate the charge of the ion formed from aluminum. Go ahead and pause the video while you work on that. So here's aluminum's orbital diagram. What is the highest occupied energy level in aluminum? Well, the highest energy level in aluminum is the third energy level. We can tell from the orbital diagram, or we can tell from aluminum's location on the periodic table. So aluminum is in the third period, or third row in the periodic table, which tells us its valence electrons are in the third energy level. Now notice something here about aluminum. It has two sublevels in its third energy level. All of the electrons in those two sublevels are valence electrons. So let's circle them. So aluminum has two electrons in its highest energy level. That's in an S sublevel. So we have a third S sublevel in the third energy level. We have one electron in the P sublevel in the highest energy level. So a total of 3 valence electrons. Aluminum will lose those to form a +3 ion. All right, let's try another one. Go ahead and draw the orbital diagram for tin. Now this one's pretty long, so I think what we'll do is we'll shorten it up. We're never going to do this except for right now. So let's start off with the valence shell for tin. What I mean by that is, let's start with 5s and then go from there. Go ahead and pause the video, please. So the highest occupied energy level in tin is the 5th energy level. Let's go ahead and again circle the valence electrons. Again, being only the electrons that are in the highest energy level. The electrons in the 4d sublevel, they're in the 4th energy level. That is not the highest energy level. Those are not valence electrons. So, any guesses what the charge of tin's ion is? Remember, tin is a metal. It's left of the zigzag. So go ahead and indicate the charge of tin. Interestingly, tin can form 2 ions, where in one situation like here, what we've shown, it has a +4 charge. That involves losing all 4 of its valence electrons, the 2 electrons from the 5s and the 2 electrons from the 5p. Sometimes tin only loses its 2 5p electrons, and it holds on to the 2 in the 5s. So if it just loses the 2 electrons from the 5p, what other charge does it form? In this case, it would be +2. Now, I don't expect you to know this yet in this class. This is something we will talk about later, where some metals can form more than one ion, tin being one of those examples. All right, let's try another one. Go ahead and draw the orbital diagrams, the complete orbital diagrams for both zinc and copper. And using the orbital diagram and the number of valence electrons, predict the charge of their ions. Now remember, copper's electron configuration isn't isn't a regular electron configuration. We talked about this earlier. It does something a little bit different. See if you can remember. Try not to look back in your notes. See if you can remember how copper's electrons are arranged. Go ahead and pause the video now. Work on those. Orbital diagrams, circle valence electrons, predict the charge of the ion. So here are the orbital diagrams. Highest occupied energy level in zinc. Biggest number I see there in the orbital diagram is 4, so the 4th energy level. Circle all of the electrons in the 4th energy level. And so zinc forms an ion with a +2 charge. Did you get this for copper? Remember, copper, one of its 4s electrons moves up to the 3d to completely fill the 3d sublevel. So copper has 1 electron in its highest energy level. It forms an ion with a +1 charge. It actually can form a second ion as well, but according to this orbital diagram, we're going to go with +1. Let me know if you would like some more examples of either excited state configurations or predicting the charges of ions by using orbital diagrams. Thanks for watching.